All right, welcome to the deep dive. Today we're going deep on embeddings and vector stores.
Ooh, embeddings.
Yeah, so for our Kaggle audience out there, think of it like this. Embeddings are like giving machines a cheat sheet for understanding the meaning of text, images, all kinds of data. It's like unlocking a whole new level of efficiency and insight.
Yeah, it's like speaking the language of AI.
Right, and with the rise of these large language models that are getting more and more powerful, embeddings are kind of becoming the secret sauce.
Yeah, exactly. They're helping us make sense of this massive amount of data that we're dealing with now. It's pretty exciting.
So our mission today is to really unpack how these embeddings work, explore different techniques, and then see how you can use them to build really cool, innovative projects. So for this deep dive, we're going to be using this excellent white paper. It's called Embeddings and Vector Stores. And it was released, let me see, just last month in February 2025. And it's by Nolgaria, Ren, and Sugnet.
A great team.
Yeah, and a bunch of other contributors. I'm not going to try to list them all here, but huge shout out to everyone who worked on this.
Yeah, there's a big list there, yeah.
Really good stuff. Okay, so let's start with the basics. The white paper does a fantastic job of breaking this down. Essentially, embeddings are like these low-dimensional numerical representations of, well, almost anything. And they're designed to capture the underlying meaning and relationships between different pieces of data.
Yeah.
So instead of dealing with like raw text or pixels, you're working with these compact vectors that preserve the essential semantic information.
Right, and that makes it way easier to process and compare huge amounts of data.
Exactly. The white paper actually uses this really cool analogy of latitude and longitude. Just like you can pinpoint any location on Earth with those two numbers, embeddings kind of map complex data into a simpler space without losing its meaning.
Yeah, makes sense.
So, all right, let's get into why this matters. Why are embeddings so important, especially for our technically minded audience?
Well, for starters, they're incredibly efficient. You can represent all sorts of data. Text, audio, images, video, even structured data like you'd find in a database. And it's not just about, saving storage space. It's about making it possible to find patterns and relationships that would be really hard to spot otherwise.
Yeah, and that's where the idea of semantic relationships comes in. The white paper explains that embeddings can actually capture how similar or different two pieces of data are.
Yeah.
So, for example, in an embedding space, the word king would be closer to queen than it would be to, say, bicycle.
Right. It's all about capturing that underlying meaning, which is pretty amazing when you think about it.
Right. So you're going from this messy world of raw data to this elegant numerical representation that actually encodes meaning. It's super cool.
Yeah. And because those embeddings are lower dimensional than the original data, they let you do large-scale processing and storage much more efficiently.
Okay, so the white paper highlights a couple of key applications where embeddings really shine. Retrieval and recommendations. What's the basic idea there?
Well, think about how Google Search works. It's a massive retrieval system, right? You type in a query, and it finds web pages that are relevant to what you're searching for. With embeddings, the process goes something like this. First, you pre-compute embeddings for billions of web pages. Then, when someone enters a search query, you convert that query into an embedding too. And finally, you find the web pages whose embeddings are the nearest neighbors to the query embedding in that vector space. And that's basically how you get your search results.
So the closer the embeddings are in that space, the more semantically similar they are.
Yeah, exactly. And recommendation systems work on a similar principle. You find items or content that have similar embeddings to what a user has liked or interacted with in the past.
So it's all about finding those patterns and making predictions based on similarity in this embedding space. Now, the white paper also mentions this concept of joint embeddings, which sounds even more powerful. Can you explain that?
Yeah, joint embeddings are all about handling multimodal data, where you have different types of data like text and images combined. So imagine you want to search for videos based on a text description. Joint embeddings allow you to map both the text and the images into the same embedding space, making it possible to compare them and find matches across those different modalities.
So it's like it's breaking down the barriers between different types of data, allowing for more nuanced understanding.
Yeah, exactly. That's a really exciting area.
So, okay, we've talked about how cool embeddings are, but how do we know if they're actually doing a good job? How do we measure their effectiveness?
Well, it depends on the task, but in general, we want to see how well they help us retrieve relevant items and filter out irrelevant ones. It's kind of like separating the signal from the noise.
And for search tasks, we often rely on these classic metrics like precision and recall, right?
Right. Precision is all about how many of the retrieved items are actually relevant. It's like, are you hitting the target? And recall tells you what proportion of all the relevant items you actually managed to find. Are you casting a wide enough net?
Right. Are you getting all the good stuff?
Yeah. And the white paper also mentions precision at K and recall at K. These are variations that focus specifically on the top K results. So, for example, precision at 5 tells you how many of your top 5 predictions were correct, which is often what we care about in practice.
Right, because nobody really goes past the first page of Google results, right?
Exactly. Now, for cases where the order of the results matters, you might use something like normalized discounted cumulative gain or NDCG.
Okay, that sounds complicated.
It's not that bad, really. The main idea is that it gives higher scores when the most relevant items are at the very top of the results list. So finding a highly relevant document on page 2 isn't as good as finding it on page 1.
Yeah, that makes sense. So a higher NDCG means you're doing a better job of ranking things in a way that's actually useful to the user. Now, the white paper also mentions these benchmarks like BER and MTB. What are those all about?
Well, those are like standardized collections of data sets and tasks that allow you to evaluate and compare different embedding models in a fair and consistent way. It's like having a level playing field.
So it helps you avoid, comparing apples and oranges.
Exactly. And the white paper suggests using these established libraries like TRX Retrieval or Pipe Retrieval to do the actual evaluation. This makes the process more reproducible and less prone to errors.
Right. It's all about having a standardized way to measure things.
Hmm.
But it's not just about those, standard metrics, is it? There are other practical considerations when you're choosing an embedding model.
Oh, yeah, definitely. The white paper lists a few key factors like model size, embedding dimensionality, latency, and cost. So, for example, a really accurate model might be great in theory, but if it's so large that it's impossible to deploy in a real-world setting, it's not going to be very useful.
Right. And if it takes forever to generate those embeddings, well, that's not going to work for real-time applications.
Exactly. You have to balance all of these factors to find the sweet spot for your particular application.
Okay, let's get a little more concrete. The white paper dives into this technique called retrieval augmented generation, or RAG, which is all about using embeddings to make language models even smarter. For our Kagglers, this is a really hot topic right now. Can you break down how it works?
Sure. The basic idea is that you use embeddings to find relevant information from a knowledge base, and then use that information to kind of boost the prompts that you give to your language model. This helps the language model generate more accurate and relevant responses. So the white paper outlines this two-stage process. First, you create an index. This involves breaking down your documents into chunks, generating embeddings for each chunk using a document encoder, and then storing those embeddings in a vector database.
So it's like you're creating this searchable library of knowledge represented by these numerical embeddings.
Exactly. Then, when a user asks a question, you go into the query processing stage. You take the user's question, turn it into an embedding using a query encoder, and then perform a similarity search in the vector database to find the chunks whose embeddings are closest to the query embedding. Those are the chunks that are most likely to contain the relevant information.
Okay, so it's like it's finding the needle in the haystack of your knowledge base.
Right. And because language models need this information quickly to generate their responses, the speed of that query phase is super important. That's where these efficient vector databases really shine.
So you're not just searching for keywords, you're searching for meaning in that embedding space.
Right. And the white paper points out how much progress has been made in embedding models, particularly Google's embeddings. Their average BER score has jumped from 10.6 to 55.7. That's huge.
Wow, that's a massive improvement. So the takeaway here is to build your systems in a way that allows you to easily upgrade to newer, better embedding models as they become available.
Yeah. And to have good evaluation pipelines in place so you can make sure that those upgrades actually lead to better results. The white paper even includes a code snippet, snippet 1, that walks through a practical example using the NF Corpus dataset.
Oh, cool. So it shows how to, actually implement this stuff.
Exactly. It shows how to embed questions and documents using Google Vertex AI APIs, how to use the FACE library for efficient similarity search, how to evaluate the retrieval quality using Pipe Retrieval with all those metrics we talked about. It's a really good hands-on demonstration.
That's super helpful. Now, one challenge that the white paper mentions is the need for labeled data to train these embedding models. That can be a real bottleneck, right?
Oh, absolutely. Getting high-quality labeled data can be expensive and time-consuming. But there are some interesting approaches emerging to address this. For example, the white paper talks about how in the development of Google's Gecko embedding model, they used large language models to generate synthetic question and document pairs for training.
Whoa, so it's like AI helping to train better AI?
Yeah, pretty much. And this can really help scale up training data and potentially lead to even better performance.
Okay, let's shift gears a bit and talk about the different types of embeddings out there. The white paper explains that the main goal is always to create these low-dimensional representations that capture the essential information, and it categorizes embeddings based on the type of data you're dealing with. So let's start with text embeddings, which are kind of the foundation for a lot of NLP applications.
Right. Text embeddings allow you to represent words, sentences, paragraphs, even entire documents as these dense numerical vectors, which is what makes them so powerful for all sorts of NLP tasks.
And the white paper divides them into token or word embeddings and document embeddings. But before we dive into those, it kind of walks through this life cycle of how text gets converted into embeddings, starting with tokenization.
Right. Tokenization is all about breaking down a text string into these smaller, meaningful units called tokens. This could be splitting by words or subword units like word pieces or even characters. Then, each unique token in your entire dataset gets assigned a unique numerical ID.
So you're basically replacing all these words and punctuation marks with numbers.
Yeah. And the white paper also briefly mentions one-hot encoding as a way to represent these token IDs as binary vectors. There's a TensorFlow example in Snippet 2 that illustrates this.
But as the white paper points out, those raw integer IDs and one-hot encoded vectors don't really capture the semantic relationships between words. That's where embeddings come in.
Exactly. So let's start with word embeddings.
Okay, so what are word embeddings?
Well, they're basically these dense, fixed-length vectors that aim to capture the meaning of individual words. You know how those words relate to each other semantically. And the white paper talks about these early breakthroughs in this area, like glove, swivel, and the super famous word2vec.
Ah, word2vec. I remember when that came out. It was a big deal.
Yeah, it really was. And the core principle behind word2vec, which is highlighted in the white paper, is that you shall know a word by the company it keeps, meaning the meaning of a word is largely determined by the words that tend to appear around it.
So it's all about context.
Exactly. And there are two main architectures for word2vec, CBOW and skipgram. CBOW, or continuous bag of words, tries to predict a target word based on the context words that surround it. Skipgram kind of does the opposite. It uses a target word to predict the surrounding words.
So which one is better?
It depends. CBOW is usually faster to train and works well for common words, but Skipgram tends to be better for infrequent words and smaller data sets. There's a good visual representation of this in Figure 5.
Okay, so you have to choose the right tool for the job.
Exactly. And the white paper also mentions fast text, which is an extension to word2vec that takes into account the internal structure of words at the subword level.
Interesting. So it's like it's getting even more granular with the meaning.
Right.
Now, one limitation of word2vec is that it mainly captures these local relationships between words within a small window of context. Glove, on the other hand, tries to capture more global information about how words co-occur in the entire corpus.
Oh, okay. So how does glove do that?
Well, it starts by building this co-occurrence matrix, which basically counts how often each word appears in the context of every other word in the entire dataset. Then it uses a matrix factorization technique to learn word vectors that encode these global co-occurrence patterns.
So, like, it's looking at the big picture.
Right. And swivel is another method that also uses a co-occurrence matrix. It's really efficient for large data sets because it's designed for distributed processing. The white paper actually includes a code snippet, Snippet 3, that shows how to load and visualize pre-trained word2vec and glove embeddings in a 2D space using GenSim and TSNE, and how to find similar words based on their proximity in this space. You can see this visually in Figure 6.
Oh, that's cool. So you can actually see those semantic relationships. Yeah, it's pretty neat. Okay, so we've covered word embeddings. Let's move on to document embeddings.
Okay, so document embeddings are all about representing the meaning of larger chunks of text, right? Like paragraphs or whole documents.
Exactly. And the white paper traces their development from these early bag of words models to the much more sophisticated large language models we have now.
So let's start with the bag of words models. The white paper mentions LSA and LDA. Can you give us the ELI5 version of those?
Okay, so LSA, or latent semantic analysis, uses a matrix of word counts in documents, and applies dimensionality reduction techniques to kind of uncover the hidden semantic relationships between words and documents. Like, it's looking for the underlying themes.
Okay.
And LDA, which stands for latent Dirichlet allocation, takes a more probabilistic approach. It models each document as a mixture of topics and each word as having a certain probability of belonging to each topic.
So it's like each document is a recipe and the words are the ingredients.
Yeah, that's a good way to think about it. And then there are TF-IDF-based models, which are statistical methods that weigh words based on how frequently they appear in a document compared to how often they appear in the entire corpus. BM25 is highlighted as a really strong baseline.
Okay, so all these bag of words models, they all kind of ignore the order of words, right? They just treat each document as like a bag of words.
Right, which is obviously a limitation. That's where .2vec came in. It's inspired by word2vec, but extends it by adding this paragraph vector to the model. There's a nice diagram of this in Figure 7. This paragraph vector learns to represent the entire document. And Snippet 4 shows how to train Doc2Vec models using GenSim.
So it's like word2vec, but for whole document.
Yeah, pretty much.
Yeah.
Now, the real game changer in recent years has been these deeper, pre-trained large language models.
Right, like BERT and all the models that have come after it.
Exactly. The white paper emphasizes the use of deep neural networks, massive amounts of training data, and this idea of fine-tuning. BERT, which was introduced back in 2018, really set a new standard. It uses this transformer architecture and was trained on these huge data sets using techniques like masked language modeling and next sentence prediction. Figure 8 illustrates this really well.
Yeah, and BERT produces these contextualized embeddings, which means the embedding for a word can actually change depending on the words around it.
Right. It's not just a static representation of the word itself. It takes into account the context.
That's super cool.
Yeah, and the CLS token is often used as a representation of the entire input sequence.
Okay.
And BERT has led to a whole family of models like SentenceBERT, SimC, and E5, which are designed to produce really good sentence embeddings. And then there are these even larger language models like T5, PaLM, Gemini, GPT, and Llama.
So many acronyms.
I know, right? But the point is that these models are getting more and more powerful, and they're leading to even better embedding models like GTR and Sentence T5. And the white paper mentions this exciting new development of embedding models powered by Google's Gemini architecture on Vertex AI, which are achieving really impressive results on benchmarks.
Wow, so embeddings are like constantly evolving.
Yeah, it's a fast-moving field. And then there's this idea of matryoshka embeddings, which let you choose the dimensionality of the embeddings based on what you need for your specific task. And for dealing with documents that contain both text and images, there are these multi-vector embeddings like Colbert, XTR, and Colpoly.
Okay, so we're way beyond bag of words now.
Yeah, we've come a long way. And the white paper does a good job of contrasting these deep neural network models with the earlier approaches, highlighting the need for a lot more data and computational resources, but also the much greater ability to understand context and meaning. Snippet 4 shows how to use these pre-trained document embedding models from TensorFlow Hub and Vertex AI, and Snippet 5 even demonstrates how to use Vertex generative AI text embeddings with LangChain and BigQuery.
So the tools are getting more sophisticated, but they're also becoming more accessible.
Exactly, and all this applies to images too, right?
Oh, right, image embeddings. So how do those work?
Well, you can get image embeddings by training convolutional neural networks, or CNNs, or vision transformers on large image datasets. The activations from one of the later layers in these models often serve as good image embeddings. They capture the learned features of the images.
So it's like the model is learning to see the important parts of the image.
Right. And then there are multimodal embeddings, which combine these image embeddings with other types of embeddings, like text embeddings, to create these joint representations that capture the relationships between different modalities. Snippet 6 actually shows how to compute image and multimodal embeddings using the Vertex AI API. And the white paper mentions Colpoly, which can even do retrieval on documents that contain both text and images based on a text query without needing to do OCR. That's pretty amazing.
Wow, that's really cool. Okay, so what about structured data? Can we create embeddings for things like tables in a database?
Yeah, definitely. Though the white paper points out that structured data embeddings tend to be more application specific because the meaning of the data is so dependent on the schema and the context.
Right, it's not as straightforward as with text or images.
Yeah. For general structured data, like a table with rows and columns, you might use dimensionality reduction techniques like PCA to create embeddings for each row. These can be used for things like anomaly detection or as input features for other machine learning models. And for user and item data, which is crucial for recommendation systems, the goal is to map both users and items into the same embedding space so you can find users and items that are similar to each other, indicating potential matches or recommendations.
So it's all about finding those hidden connections.
Right. And you can even combine these structured embeddings with unstructured embeddings like product descriptions or user reviews to create even richer representations.
Now, the last type of embedding that the white paper mentions is graph embeddings. This is where things get really interesting because now you're not just representing individual data points, you're representing relationships.
Exactly. Graph embeddings are all about representing objects and their relationships within a network. Like, think of a social network where people are nodes and connections are edges. A graph embedding for a person would capture not just their attributes, but also their position in the network and who they're connected to.
So it's like it's encoding the social fabric. Yeah.
Right. And you can use this for all sorts of cool things like predicting who might know each other, categorizing users, and building graph-based recommendation systems. There are a bunch of algorithms out there like DeepWalk, Node2Vec, Line, and GraphSage.
So many algorithms, so little time. Okay, we've talked about all these different types of embeddings. Let's get into how they're actually trained. What's the typical process?
Well, many modern embedding models use this dual encoder architecture. There's an encoder for the query and an encoder for the documents or images or whatever you're working with. And they're trained using contrastive loss, which basically tries to pull the embeddings of similar data points closer together while pushing dissimilar ones farther apart.
So it's like attracting the good stuff and repelling the bad stuff.
Yeah, that's a good way to think about it. And the training usually involves two main stages, pre-training and fine-tuning. Pre-training is all about training the model on a massive data set to learn these general representations. And it's becoming really common to initialize these models with weights from these huge foundation models like BERT, T5, GPT, Gemini, and Coca. This lets the embedding model benefit from all the knowledge that's already been learned during that pre-training phase.
So it's like it's getting a head start.
Right. And then you fine-tune the model on a smaller, task-specific data set to really dial it in for your specific application. And there are a bunch of ways to create these fine-tuning data sets. You can do manual labeling, or you can generate synthetic data, or you can use techniques like model distillation or hard negative mining.
A lot of options there.
Yeah. And once you have these trained embeddings, you can use them for all sorts of downstream tasks. Like, if you want to build a classifier, you can just add a classification layer on top of the embedding layer and train it.
And you have a few options there, right? You can freeze the embedding model, or you can fine-tune it along with the new layers.
Right. It depends on how much data you have and how specific your task is. Vertex AI actually provides some really cool tools for customizing and fine-tuning text embedding models. And Snippet 7 shows how to build a classifier using a trainable layer from TensorFlow Hub.
Okay, so we've got our embeddings. Now, how do we actually search through them efficiently at scale? That's where vector search comes in.
Yeah, vector search is all about finding items based on their meaning, not just on matching keywords. So you compute embeddings for all your data, store those embeddings in a vector database, then embed your query into the same space, and find the data items whose embeddings are closest to the query embedding.
Okay.
And because we're often dealing with huge data sets, we need to use approximate nearest neighbor, or ANN, search techniques to speed things up.
Right, we can't just compare our query embedding to every single embedding in the database. That would take forever.
Exactly. ANN methods let us find really good matches really quickly, even with millions or billions of data points.
So what are some of these ANN techniques?
Well, the white paper talks about locality-sensitive hashing, or LSH, and tree-based methods. LSH uses these hash functions to map similar items to the same bucket, so you only have to search within those buckets. The white paper uses this analogy of postal codes, which is pretty helpful. Tree-based methods like KD trees and ball trees work by recursively partitioning the data space. Snippet 8 actually demonstrates using brute force search, ball tree, and LSH with scikit-learn and Zelshing.
Oh.
And there are also techniques that combine hashing and tree-based approaches, like FAISS with HNSW and SCAN.
Okay, let's talk about HNSW. What's that all about?
So HNSW, which is part of the FAISS library, builds this hierarchical proximity graph. It starts with these long-range connections to quickly get you in the right neighborhood, and then it uses shorter-range connections to refine the search. Snippet 10 shows how to use face with HNSW, and Snippet 9 even shows how to build an ANN index with Vertex AI vector search, which also uses HNSW, and how to integrate it into a RAG pipeline with LangChain.
So HNSW is like the go-to algorithm for a lot of applications.
Yeah, it's a really solid performer. Now, Google has this other technique called SCAN, which stands for Scalable Approximate Nearest Neighbor. It's used in a lot of Google's products and is available through Vertex AI Vector Search and Google Cloud databases. For really large data sets, it can even do this partitioning step to further speed up the search.
So it's breaking down the problem into smaller, more manageable chunks.
Right. And then it uses a combination of scoring techniques to find the best matches. Snippet 11 shows how to use SCAN with TensorFlow recommenders.
Okay, so we've got all these cool algorithms for searching through embeddings, but we need specialized systems to manage all of this at scale. That's where vector databases come in.
Right. Traditional databases weren't designed for this kind of high-dimensional data and similarity-based queries. Vector databases are built specifically for this purpose.
So it's like they're purpose-built for the world of embeddings.
Exactly. And the white paper mentions that even traditional databases are starting to add vector search capabilities, which is called hybrid search. Figure 16 shows the typical workflow. Embed your data, index the vectors, embed your query, and then search for similar items.
Makes sense.
And there are a bunch of options out there. Vertex Vector Search, AlloDB, and Cloud SQL for PostgreSQL with extensions for vector search, Pinecone, Weaviate, ChromeDB. They all have different strengths and weaknesses, so you have to choose the right one for your needs.
So it's a growing ecosystem.
Yeah, it's really exciting. And the white paper also talks about some of the operational considerations when you're working with embeddings and vector stores at scale.
Right, because it's not just about the algorithms, it's about the whole infrastructure.
Exactly. There are challenges with scalability, availability, consistency, updates, backups, security. And the white paper emphasizes that embeddings themselves can change over time as the underlying models are updated, so you need to think about how to manage those updates and re-index your vector store.
It's a lot to keep in mind.
Yeah. And the white paper also points out that embeddings might not be the best way to handle every type of information. Sometimes you might need to combine them with traditional full-text search techniques.
So it's about choosing the right tool for the job.
Exactly. Okay, so we've covered the basics of embeddings, the different types, the training process, the search algorithms, the vector databases. Now let's talk about the applications. What can we actually do with all of this?
Right, because that's what really matters in the end.
Absolutely. The white paper summarizes a whole bunch of applications. Information retrieval, recommendation systems, semantic text similarity, classification, clustering, re-ranking. And when you combine embeddings with vector stores and ANN search, you can build even more powerful applications like RAG, large-scale search engines, personalized recommendation systems, anomaly detection, and even few-shot classification.
Okay, so there's a lot you can do.
Yeah, the possibilities are pretty much endless. And the white paper highlights how embeddings are often used in the first stage of ranking for these large-scale applications to quickly narrow down the search space. ANN techniques like SCAN are really good at this. And then, of course, there's ARG, which we talked about earlier. It's a really powerful way to make language models more accurate and less prone to hallucinations.
Yeah, RAG is definitely a game changer.
Right. And the white paper also stresses the importance of providing sources for the information that the model retrieves so users can verify things and trust the results more. Figure 17 shows a good example of this.
Okay, so the key takeaway here is that embeddings and vector stores are incredibly powerful tools, but you need to understand their strengths and weaknesses and choose the right combination for your specific needs.
Yeah, and for our Kaggle audience out there, this is a really important skill set to develop because it's going to become even more critical as language models get more and more powerful.
So we encourage all of you to dive deeper into the white paper, explore the different tools and techniques, and start experimenting. See what you can build.
Yeah, with the advancements in embedding models like the Gemini-based models and vector search algorithms like SCAN, we're just scratching the surface of what's possible.
Who knows what kind of amazing applications will be built in the next few years. So go out there and build the future. Thanks for joining us for this deep dive.